And let's illustrate that with an example. 3.4.12 has the object as a bullet. Story is, a .45 caliber bullet shot straight up from the surface of the moon would reach a height of 832 t minus 2.6 t squared feet after t seconds. So straight up, so it's movement along a vertical axis. They're measuring position in feet and time in t. So velocity will be in feet per second. On Earth, in the absence of air, the height for a similar situation is s equals 832 t minus 16 t squared feet after t seconds. So similar formats for the heights, only difference is these coefficients of t squared, and we'll see why that's the case here shortly. Question is, how long will the bullet be aloft on the moon and on the Earth in each case, and how high will the bullet go? Okay, to find out how long the bullet is aloft, we'll set the height equal to 0. So that'll give us 2 times. The bullet at time t equals 0 is at ground level, then it goes up, and it comes back down, and it's at ground level again. So simply take the height on the moon, 832 t minus 2.6 t squared, set it equal to 0, and solve for t. We can factor a t out, giving us t times 832 minus 2.6 t. Set both factors equal to 0, t equals 0 seconds. I told you so, it's when it's at ground level, when everything starts, when the gun's fired. And set the second factor equal to 0. Rearrange, we'll get t equals 832 over 2.6, that's 320 seconds. Nice numbers. So they've massaged the numbers for us, apparently, to give us nice integer values for t of 0 seconds and 320 seconds. How long was a bullet aloft? 320 seconds. Started at 0, 326 seconds later, it's back down to ground level on the moon. Surface of the Earth, same problem, different formula. This time 832 t minus 16 t squared equals 0. Factor t out, we get t equals 0 just like before. Set this factor equal to 0, we get t equals 832 over 16, which reduces to 52 seconds. So the bullet's aloft on the surface of the Earth, 52 seconds. The ratio between these two is about 6 to 1. 6 times 52 is not precisely, but roughly 312. 320 is it is 312, but it's close. This is because you may have heard it said the moon has 1/6 the gravity of the Earth. Little round off error, but we're in the ballpark there. Next, they want to know, and this is very conceptually important. They want to know how high did the bullet go. Okay. There's more than one way to do this. We're going to do it like this, foreshadowing applications of derivatives to graphs in chapter 4. Think like this. Think like this. The bullet goes up when the velocity is positive. It stops when the velocity is 0, and then it falls when the velocity is negative. So we can find the time when the bullet was at its highest point by setting the velocity equal to 0. That's when it's at its maximum height. And then we can use that when time to find the what height, to find what the maximum height is. So it's based on the elementary idea that it goes up, it stops, and then it comes back down. When did it stop and turn around and come back down? When the velocity was 0. Going up, velocity is positive. Going down, velocity is negative. When it reached the top, it stopped having a positive velocity, started having a negative velocity, and was 0 in between. That idea is going to make so much stuff work when we start using derivatives to graph functions. Okay, so we're going to set the velocity equal to 0, and that'll give us the when it was at its maximum height. On the moon, velocity function is, differentiate that formula, 832t gives us 832 minus 2.6 t squared, bring the 2 down, subtract 1 gives us negative 5.2 t. Units will be feet per second because it's a velocity. So when's the velocity? 0. Set the velocity equal to 0, set 832 minus 5.2 t equal to 0. Solve for t, we get 832 over 5.2, we get 160 seconds. So that's when the velocity is 0. That's when it stopped going up and started going down. How high is it at that point in time? Well, I know when, and I know height is a function of time. Here it is on the moon. So we'll plug t equals 160 in. We'll get 832 times 160 minus 2.6 times 160 squared. This is height. The units will be feet. Crunch the numbers. We get 66,560 feet, which is like 12.61 miles. Not that that's terribly relevant, but that's the concept behind it. Set the derivative equal to 0. That's where you'll have that maximum height. Find the time based on 0 velocity and use that to find the corresponding height. On the Earth, same thing. We'll take the formula for position, differentiate it. This will give us velocity. Set that velocity equal to 0. 832 minus 32t. Set equal to 0. Implies t is 832 divided by 32, which is a nice round number of 26 seconds. So the maximum height on the Earth is, take the height function as given here, plug in t equals 26. We get 832 times 26 minus 16 times 26 squared. Crunch the numbers. It's a height. It'll be in feet because that's the units we're using. It'll be 10,816 feet, a little over 2 miles. Now, think like this. We set the derivative equal to 0 because we knew the function described something that went up, stopped going up with 0 velocity, and then started going down. And we found the time based on that. That's how we'll use this in the future. But if you think about it and look at the numbers, well, the absence of air resistance, it kept things nice and symmetric. It went up half the time, and then it went down the other half of the time. And indeed, we know how, part A told us, how long the bullet was aloft. What was the answer? Let me go back. On the moon, it was aloft 320 seconds. So half that time it was going up, and the other half it was coming down. So when did it reach its maximum height? Should have been half this, should have been 160 seconds, and it was. On the Earth, 52 seconds aloft. You know, half of that's 26. It was going up 26 seconds, and it was coming down 26 seconds. So we should have gotten 160 seconds and 26 seconds, and we did. 160 seconds and 26 seconds was when it reached its maximum height. Oh yeah, given that information we had from the first part, we didn't have to go through this setting the velocity equal to 0 if you'll think about it in terms of symmetries. I want to think about it like this, of setting that velocity equal to 0, because that's a big conceptual idea. But there was an alternative way to do it. But this is the way I want to think about it in terms of how we'll apply derivatives later. Okay, back to the notes. And a little bit more Galileo stuff. We mentioned Galileo, I think it was section 2.1. In exploring the velocity and acceleration of an object experimentally, Galileo rolled balls down an incline ramp. His plan was to have an object fall at an angle so that the speed of fall would be slower than when the object was in free fall. So he's trying to find a relationship between time and distance. In this way, he could better measure the time it took the object to move a certain distance. So when you just drop an object, it's pretty difficult to time how long it took it to fall a certain distance. Remember, Galileo, he's working with a pendulum clock here. This is 400 odd years ago. So he ain't got a stopwatch. He's trying to measure things. He uses pendulum clocks. He actually uses his pulse to measure certain things in some of his experiments. His notebooks are still around. They're still in print, in fact. So what he did was roll balls down inclined planes to slow down their vertical motion and relate that to what we get in terms of free fall. These experiments are described on this website, NOVA, Galileo's Inclined Plane. Available from PBS learning media site of, so get this, I actually found this on East Tennessee PBS, probably out of Knoxville. And exercise 3.4.14 has you quantitatively deal with this. We stated a formula by Galileo in section 2.1, and this is where that formula come from these experiments. Here's Galileo describing the experiments in his own handwriting from 1604, I guess is when this was done. This image I've used before is from something called the Mac Tutor History of Math Archives, an excellent site for history of math stuff. This little image here, the only place I could find that image was a History of Science publication. Here's the reference on it. It's there's a link there to this online as well. It's also rumored, keyword being rumored, that Galileo did a similar experiment by dropping objects off the Leaning Tower of Pisa. This is more mythology than anything. The story is from a biography of Galileo by one of his students, Vincenzo Viviani, written in 1654, published in 1717. Yeah, this is probably just more of a mythological thing. He was from Pisa, so he studied falling objects. Makes sense he'd use the Leaning Tower of Pisa, but it's probably just a story. The Wikipedia page about Galileo and the Leaning Tower of Pisa, there's a link there. Not that Wikipedia is the world's most authoritative source on this kind of information. Back here, we're looking at a refereed science publication in the history of science. So this you can depend on as being reliable. Wikipedia, it has links to other references. So it's a good place to go to look for other things. Don't take Wikipedia as the necessarily entirely 100% accurate. But I bring this up because exercise 3.4.13 deals with a story about Galileo dropping cannonballs off of the Leaning Tower of Pisa. Question 13 is worded, had Galileo dropped a cannonball from the Tower of Pisa, and so forth. My emphasis on had, but you can tell right there the authors of the textbook are not claiming this actually occurred. It's a piece of cake to set up the physics formulas for what would happen had this occurred. But let's look at exercise 14, which deals with this inclined plane stuff. And here's the story. We'll have a picture on the next slide. It says, Galileo developed a formula for a body's velocity during free fall by rolling balls from rest down increasingly steep inclined planks and looking for a limiting formula that would predict a ball's behavior when the plank was vertical, and so the ball was falling freely. We got a picture below of exactly that. They've introduced an angle theta in the picture, as we'll see. He found that for a given angle of the plank, we'll denote it as theta, the ball's velocity t seconds into motion was a constant multiple of t. So velocity is a constant multiple of t. In symbols, we'd write the velocity, so here using what the book has, but here they'd write that the velocity was represented by k times t for some constant k. The value of constant k depended only on the inclination of the plank. It'll depend on the angle theta, as we'll see. In modern notation, with distance in meters and time in seconds, what Galileo determined by experiment was that for a given angle theta, the ball's velocity t seconds into the roll was y equals 9.8 sine theta times t meters per second. We're measuring velocity here. All right, so here's what they're saying. He had these planks at an angle, theta being the angle with the horizontal. He rolled the ball down the plank. It's going to have smaller velocity rolling down a slightly inclined plank as it does rolling down a greatly inclined plank. And the idea was as theta gets bigger, he's more closely approximating free fall. So he's looking for a formula to describe free fall. And he does it because of the experimental limitations he has, which is really just the presence of a good clock to time things. He does this with inclined planes. Questions are, what is the equation for the ball's velocity during free fall? And building on your work from that, what constant acceleration does a freely falling body experience near the surface of the Earth? Okay, well, we're all set to deal with that. I mean, the real punchline on the math part is they told us velocity is given by 9.8 sine theta times t. We'll fix theta, and then that will determine what we get for this relationship for velocity as a function of time. Free fall, they wanted to know during free fall. Well, during free fall, this angle theta is going to be pi halves, 90 degrees. So the ramp becomes irrelevant when you make it vertical, and then you just have the object free falling. So he experiments with small angles and he deduces this idea. So we'll take theta to be pi over 2. It's calculus class. We're going to measure angles in radians. Sine of theta, then the sine of pi halves is 1, and the velocity function just becomes y equals 9.8 t. The sine theta part is 1 when theta equals pi halves. They wanted the equation for velocity. There's the equation for velocity as a function of time. Next, they want us to determine acceleration at the surface of the Earth. Okay, well, we know acceleration is a derivative of velocity, and here's velocity right here. Acceleration is derivative of velocity. It's what we define acceleration to be. We know the velocity is 9.8 t of meters per second. Differentiate that. We'll get just simply 9.8. The units will be meters per second squared. If you're familiar with units used to measure position, velocity, and acceleration. If you ain't, let's look at that units thing a little bit. Not such a big deal in a math class. I think it probably should be, actually, but it's usually played down in a math class. It's a very big deal in a physics class. So let's get you ready for them physics and engineering classes. Were we to take a difference quotient to calculate this derivative of velocity with respect to time, we'd take a limit as h approaches 0 of this difference quotient. It'd be velocity at time t plus h minus velocity at time t over h. Velocity is measured in what? Meters per second. Meters per second. H is time. It's measured in seconds. So we'd have meters per second divided by seconds would yield meters per second squared, as you'd expect for acceleration. So the units are legitimate, and they do come out of keeping up with units throughout the computations, which I'll probably not frequently do. I'll definitely keep up with units when I state the final answers, but within the computations on these slides, it gets kind of cumbersome to keep up with units. But definitely when writing out final answers. So for an object in free fall at the surface of the Earth, we have the acceleration is 9.8 meters per second squared. Right. If we treat acceleration as a vector quantity, just a little free education here, with up as positive and down as negative, we might say the acceleration due to gravity at the surface of the Earth is negative 9.8 meters per second squared. Yeah, acceleration should be expressed as a vector quantity, and this is a more appropriate way to describe acceleration due to gravity at the surface of the Earth. The question up here was subtly different, and that's why there's not a negative sign on there. But you're prone to see these negatives pop up, and we'll do it here shortly, in fact, pop up in the equations of motion. If we measure distance in feet instead of meters, then we find that the acceleration due to gravity at the surface of the Earth is 32 feet per second squared down, or if you like, negative 32 feet per second squared. And if we measured distances in feet, we'd find that velocity is 32t, and that distance is 16t squared. The distance an object falls in a time t is 16t squared. Hey, that's exactly the same formula we had in section 2.1, this 16t squared thing, when we talked about average rates of change back in the beginning of chapter 2. So that's where that Galileo formula comes from, by the way. Back to the notes. Some more mechanics. Okay, let's state some general formulas in terms of heights of objects. So this totally deals with an object moving up and down. The idea being maybe I threw something straight upward. It went up, it stopped, it came back down. At the surface of the Earth, if an object is fired directly upward with an initial upward velocity of v sub 0 from an initial height s sub 0, then the height of the object at time t is s of t equals negative 16 t squared plus v sub 0 t plus s sub 0. Well, there's Galileo for you right there, the 16 t squared part at least. And at firing the bullet on the moon, we had another term here. We had a constant multiple of t, it was 832 t. That represented initial velocity. It was the same on the Earth as it was on the moon, because they're firing the same gun, presumably on the surface of the Earth as the surface of the moon. And we didn't have a term over here. Yeah, we were standing on the surface of the Earth or the surface of the moon. So there wasn't an initial height or an elevation off the surface. So if you look back at the firing the bullet, we had exactly that form on the surface of the Earth. We had a different coefficient here when we dealt with firing the gun on the surface of the moon. It's because there's a different acceleration due to a different gravitational pull on the surface of the moon. But on the surface of the Earth, this is what we get. If we measured distance in feet and time in seconds. So that negative 16 is related to the negative 32 feet per second squared acceleration due to gravity at the surface of the Earth, feet per second squared. If we measured distances in meters, then we'd have to do a little conversion, and then you get equations of the form negative 4.9 t squared plus v sub 0 t plus s sub 0, initial velocity times time plus initial position. We're stating this authoritatively at this stage. We could actually work backwards from constant acceleration and derive these formulas once we know how to do something called anti-differentiation. We ain't quite finished with differentiation yet. But establishing these formulas is not complicated, though you do need to know some anti-differentiation. The level of anti-differentiation it requires is not very sophisticated. You could probably guess these formulas based on what you know now, but a story for another day. We can take these formulas and differentiate them. If we found say the acceleration at the surface of the Earth, we take the derivative of the derivative of position. The derivative of this position would be negative 32t plus v sub 0. You lose the constant over here. You lose the t on differentiation, gives a 1. You get negative 32t plus v sub 0. That would be the velocity as a function of time. If you differentiate that to get acceleration, you'll just be left with negative 32. The units will be feet per second squared if we use this formula. And if we differentiate this twice, you'll be left with negative 9.8 meters per second squared. These two numbers, 32 feet per second squared and 9.8 meters per second squared, plus or minus, should ring a bell. That's the acceleration due to gravity at the surface of the Earth, depending on whether you measure distances in feet or meters. Let's look at a couple more examples. Okay, story here. This is an example from the book. It says, a dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second. Yeah, they tell us what it is in miles per hour. So let's not get into that. Let's stick with feet and seconds. We could do some unit conversion if they make us. It reaches a height of s equals 160t minus 16t squared feet after t seconds. Part A, how high does the rock go? Piece of cake. We'll work that one just like we did the bullet on the surface of the moon and the surface of the Earth. I mean, it's dynamically, it's the same question. What are the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? Here's a little schematic of what happens. There's an explosion, the rock flies up in the air, goes up, it stops, it turns around and comes back down. So it reaches a height of 256 feet apparently on the way up. It goes higher than that apparently. I don't know, we have to crunch the numbers. It turns around, comes back down, and it reaches a height of 256 feet again. We'll want to figure out when that is, probably. What's, what's the acceleration of the rock at any time t during its flight? And when does the rock hit the ground again? Okay, these last two are actually the easier ones to answer, but here's what happens. So up, stops, back down. Let's approach this the same way we did firing a gun on the surface of the earth. All right, so like the firing of the gun example, we know the rock goes up with positive velocity, it reaches a maximum height, then the velocity is 0, and then it falls with negative velocity. How high does a rock go? Okay, they gave us height, so we'll find velocity by differentiating. Differentiate height, differentiate position. 160t minus 16t squared, derivative is 160 minus 32t. We'll set that equal to 0, as we did before, and we'll solve for t, t equals 5. So at 5 seconds, it reaches its maximum height. It went up. At 5 seconds, the velocity was 0, and then it starts to come back down. By the way, it was a loft 10 seconds. We'll do that here to answer the latter parts. How high was it then at 5 seconds? Well, we'll just take the height function, plug in 5. It's 160 times 5 minus 16 times 5 squared. Here it is. Crunch the numbers, then you get 400. Units will be feet because it's height. So how high does the rock go? Maximum height's 400 feet when the velocity was 0. What are the velocity and speed of the rock when it's 256 feet above the ground, on the way up and on the way down? All right, well, same idea. We'll have to figure out when it was at that height. So we'll take the height function, 160t minus 16t squared, and we'll set it equal to 256 and solve it and hope they've given us nice numbers. So solve for t, should get two values. Let's get the variables on the right-hand side. That'll produce this quadratic. Feel free to pause the video and double check the arithmetic, make sure it's okay with you. But we'll get 16t squared minus 160t plus 256 equals 0. Turns out 16 divides all of those, so they probably did give us nice numbers. And we can simplify that to t squared minus 10t plus 16 equals 0, dividing that factor of 16 out. And this you should be able to factor. So that's not bad. That's t minus 2 times t minus 8 factored, set equal to 0. So we get t equals 2 seconds and t equals 8 seconds from those two factors. Yeah, that makes sense. 2 seconds, it must have been going up, and at 8 seconds, it was coming back down. When did it reach its maximum height? At 5 seconds. Hey, look at that. 2 seconds to 5 seconds is 3 seconds. And 5 seconds to 8 seconds is also 3 seconds. There's this symmetry that it has. It was started going up at 0, hit ground at 10 seconds later. Halfway through that was the maximum height. And then we've got the same distance of a height of 256 on both sides of that time of 5 seconds. There's a lot of symmetry to this, it turns out. Not that they ask about it. But we get 2 seconds and 8 seconds is when it has a height of 256. Let's find, they wanted the velocity and the speed at those times. Okay, velocity, v of 2, velocity at time 2 when it's going up, is, we got the velocity function, here it is, 160 minus 32t. We'll plug in t equals 2, do the arithmetic, we'll get 96 feet per second, so that's velocity when it's going up. When it's going down, we'll plug in 8. 160 minus 32 times 8, we get negative 96 feet per second on the way down. That makes sense. It's that symmetry thing again, except it's going up with positive velocity here, and it's going down with negative velocity here. And the speed, they ask us about the speed as well. Speed is the absolute value of these, and at both times, up and down, the speed's 96 feet per second. Yeah, there's that symmetry to it as well. Something they didn't ask us about, but we could easily figure out is how fast is it going when it hits the ground? It'd be negative because it's going down. We could ask a question about firing that gun on the surface of the Earth or the moon and ask how fast is a bullet going? What's the velocity or speed when it hits the ground? You know, I'd expect that by this symmetry that we've observed, I'd expect the initial velocity to equal that final velocity when it hits the ground. With a gun, it's called a muzzle velocity. So we could actually figure those things out using this calculus stuff as well. But there's what we get for velocity going up and coming down, and for the speed. That's the real calculus stuff. They wanted some other things. They wanted, this is calculus as well. They wanted the acceleration at time t. Okay, easy enough. We'll take the second derivative of position. The first derivative is 160 minus 32t. We just use that. That's the velocity. So differentiate the velocity and we get negative 32. Units will be feet per second squared. Yeah, you kind of knew that was coming because we're talking about movement at the surface of the Earth. So there's acceleration. It's a constant. When does a rock hit the ground again? When you think it's going to hit the ground. It took it 5 seconds to reach its maximum height. So it's going to hit the ground at 10 seconds, 5 seconds later when it comes back down. We can analyze that the way we did earlier by taking the height, 160t minus 16 squared, and setting it equal to 0. Factor 16t out this time. We get t equals 0 and t equals 10. So the rock hits the ground at t equals 10 seconds. Started at ground level at t equals 0. There was an explosion. It was given an initial velocity. We could figure out what that is with the information we have and the knowledge we have. And then it reached a maximum height 5 seconds later, and it came back down and hit the ground a total of 10 seconds later. The symmetry makes perfect sense, and I've made an observation about the symmetry in terms of the heights and the velocities is given there. Yeah, this is really not a calculus question here, at least not as we've worked it. We could have maybe used some of the earlier calculus information to draw this conclusion perfectly logically well. Okay, let's see. We want to do this one now. I think we do. Yeah, let's look at the next question as well, which says here is the graphs of position, velocity, and acceleration of a body moving along a coordinate line as functions of time. Which is which and why? Okay, so one of these apparently is position. We've got an object moving along a line. Here's what you don't want to think. You don't want to think, well, maybe that's position and the particle, it moves like this. No, it's not moving in 2 dimensions. Remember, this is a graph of location versus time. The particle doesn't move like that. The particle moves along a line. Maybe it moves along a horizontal line. Maybe it moves along a vertical line. I don't know, it moves along some coordinate line. And its position is given by the y-coordinate of one of these points, maybe here. If A is position, then we've got position 0 at whatever time this point yields. And they didn't give us calibrations on the axes, so I don't know what the times are. If this is position, and I don't know that it is yet. All right, so these are graphs of position as a function of time, velocity is a function of time, and acceleration is a function of time in some particular order. These are not the trajectory that the point takes. That's something a little more subtle. All right, so hey, the rate of change of position is velocity, and the rate of change of velocity is acceleration. So we want to think about these in terms of derivatives, one of the other. So what's it going to be? How about this? When A is negative, B is decreasing. A is negative for these values of time. A, the blue curve, below the axis, between this time equals 0 and whatever time we have here. Hey, and for those time values, the B function is decreasing. I want to talk about rates of change, because that's what derivatives are. We've got negative blue curve and decreasing, what's that, yellow curve? Starting here, going to this final time over here, we've got this one positive, and now we got B increasing. Hey, also, when the A curve is 0, the B curve has a horizontal tangent line. And we've talked about horizontal tangent lines. They're where the derivative is 0. Sounds like A is acting like the derivative of B. The rate of change of B seems like it's given by A. The rate of change of curve B is curve A. Okay, so we've decided that's consistent. I mean, I'd kind of worry about some other things being consistent as well. They only gave us 3 curves, so we only got 3 things to choose. And one is the derivative of the other, and the third is the derivative of one of the remaining. So it's certainly consistent that since this is negative when that's decreasing, this is 0 when that has a horizontal tangent line, this is positive when that one's increasing. Very much consistent that the derivative of whatever this is given by that. So maybe we've got that this is position and this is velocity. Maybe. We got to drag C into the picture and see if C is the rate of change of one of these, or if one of these is the rate of change of C. What you notice about C? How about this? It's always decreasing. It's always going downhill, except maybe right at the endpoints. Looks like it's got horizontal tangents maybe at the endpoints, but other than that, it's going downhill. So the derivative of C would always be negative. Hey, look at this. B is always negative. Not only that, but at time 0, B is 0, and C has a horizontal tangent line. At this last time point over here, B is 0 again. Hey, look at that. C has a horizontal tangent line again. Sounds to me a lot like the derivative of whatever this quantity is represented by quantity B. The derivative of curve C is curve B. So here's what we've got. If you buy those arguments, then we have the derivative of curve C is curve B. The derivative of curve B is curve A. That's what we argued on the previous slide. So if I got to match these up to position, velocity, and acceleration, we must have position, velocity, and acceleration. The rate of change of position is velocity. The rate of change of velocity is acceleration. These must be position, velocity, acceleration. C, B, and A, respectively, is written down here in the little box. Okay, so derivatives are rates of change. Velocities are rates of change of position because they're derivatives of position. Acceleration is a rate of change of velocity because acceleration is a derivative of velocity. By looking at the graphs and thinking about slopes of tangent lines and increasing and decreasing, positive and negative velocities, or rates of change more generally, then I can patch together an answer to this question. Back to the notes, I think one final little idea. Yeah, an economics application. So not to make it all physics. In economics, the term marginal is used when referring to derivatives. We might talk about marginal profit, marginal revenue, marginal cost. It just means derivative. If a company produces and sells a number X of objects, so X counts the number of objects, and the cost of producing those objects is C of X, and the revenue that results from selling them is R of X, then the resulting profit is P of X equals R of X minus C of X. So you're making X objects. It costs you C of X to make that many objects, production costs. You make an amount of money, R of X, from selling those X objects. So it's cost you C of X, you've made from it R of X, so revenue minus cost, that'll give the profit, the money you've made or lost if it's negative, off of producing and selling X of these objects. The functions, P prime of X, R prime of X, and C prime of X are called marginal profit, marginal revenue, and marginal cost functions, respectively. So when you hear marginal in this economic setting, it just means derivative. So just a vocabulary thing. You're good at taking derivatives. So suppose that revenue from selling X washing machines is given by R of X equals 20,000 times 1 minus 1 over X, revenue measured in dollars. Find the marginal revenue when 100 machines are produced. So that means, what's the derivative of R evaluated at 100? So what's R prime of 100? Not complicated. We can differentiate that, and then we'll plug 100 in. Keep an eye on units too. Use the function R prime of X to estimate the increase in revenue that will result from increasing production from 100 machines per week to 101 machines per week. And this is a new idea. I'm sort of foreshadowing some things we'll see right at the end of chapter 3. You might be a little bit uncomfortable with what we do here. It's one reason I'm doing it. That's my job, eh? But we'll recycle these ideas around the end of the section and spell them out in more detail then as well. So if part B, the answer bugs you a little bit, I kind of agree with you with how the things we've defined at this stage. And part C, they want us to find the limit of R prime of X as X approaches infinity, and they want us to interpret it. All right, I ain't worried about this first part. It's a derivative. I ain't worried about this last part. It's a limit. As X approaches infinity, it's a horizontal asymptote type question. Okay, well, part A, let's see, they want the marginal revenue when 100 machines are produced. Marginal revenue is a derivative. So we'll differentiate the revenue function, differentiate R of X, differentiate this. We can bring the constant out front, derivative of 1 minus 1 over X. I can use the quotient rule on that. Maybe a little bit easier if I just write that as X to the negative 1, and then I just got to use the power rule for negative integers. So let's rewrite the 1 over X as X to the negative 1 because the differentiation is a little bit easier. Derivative of 1 is 0, didn't even write it. A little careful with the negatives here. We'll have negative, bring the negative 1 down and subtract 1 from the exponent. That'll give us negative 1, X to the negative 2. There's the exponent that's been brought down. There's a negative sign that was out front right there. And we subtracted 1 from negative 1, yielding a new exponent of negative 2. Okay, let's clean that up a little bit. I mean, that's the derivative, but we're going to have to plug 100 into it. So we get negative times negative. We get 20,000 over X squared. There's the revenue function. Units would be revenue was measured in terms of dollars. X was in terms of what X counted washing machines, number of washing machines. So the units of this revenue function would be 20,000 divided by X squared. Dollars per machine is what we get out of this. Okay, let's see. They wanted us to deal with R prime of 100. We'll do that next. They say use R prime of X to estimate the increase in revenue that will result from increasing production from 100 washing machines per week to 101. I still owe you the plugging in 100. This is actually the answer to part A. The rate of change of revenue at X equals 100 machines is R prime of 100. Plug 100 in, we had 20,000 over X squared. X is 100, produces 20,000 over 10,000. That'd be $2 per machine were the units. So there is the marginal revenue function evaluated at 100. There's the answer to part A. I should have that in a box, actually. So what's up with this about going from 100 machines to 101 machines? Well, the slope of the tangent line, because this is a derivative, to the revenue function at X equals 100 is 2. Derivatives are slopes of tangent lines. So here's a rise over run estimation for the function R of X at 100. It's a slope of a tangent line is what it is. So this is the part I'd say is a little bit loose in terms of the applications. So what we're going to do is say, hey, if X changes from 100 machines to 101 machines, that is, if the change in X, delta X is 1 machine, how does the revenue change? Well, the rate of change of the revenue at 100, we just saw was $2 per machine. So if we have a rate of change of $2 per machine, and we change the number of machines from 100 to 101, so we've changed it by 1, we've raised it by 1, then this delta X quantity is 1 machine per week. They slipped per week into the production time schedule on this. So we'll take the rate times the change in X. Notice we've got dollars per machine for R prime. We'll have machines per week for the change in X. X measured machines per week, it sounds like, from what they've described. The machines cancel, and we'll get $2 per week out. So we get $2 from the multiplication of the numbers, and we get, we get 2 for the multiplication of the numbers. We get dollars per week out in terms of the units for what we produce here, in terms of a change, increase in revenue that results from that type of change in the number of washing machines produced. This idea of taking an instantaneous rate of change and multiplying it by a specific change in the input value to give an approximate change in the original function, we'll see a lot more of that at the end of chapter 3. For now, let me just introduce this as kind of a foreshadowing. We'll do one more example that's related to this as well. They ask us what's up with the marginal revenue as X approaches infinity, and what's it mean to you? Well, we'll take a limit as X approaches infinity of marginal revenue. That's what we had for marginal revenue. Okay, we can bring the 20,000 out front. Then we'll have a limit of 1 over X squared. We can write that as a limit of 1 over X, quantity squared, back when we did infinite limits, the end of chapter 2, wasn't it? I guess it's a constant multiple rule and the power rule from theorem 2.12 that we've used to establish those two things. The constant comes out front, and we've taken the limit inside that squaring function. And you don't know much about infinite limits, but you know the limit as X approaches infinity of 1 over X, you know that goes to 0. So we get 20,000 0 squared, which is just 0. So the limit as X approaches infinity of R prime of X is 0. So the number of washing machines, as the number of washing machines, that is as X, gets larger and larger, the revenue increases. I mean, R prime is given by this, 20,000 over X squared. When X is positive, well, as long as X ain't 0, that's positive. So R prime is positive. The revenue increases. When you make more washing machines, revenue goes up. The thing is, it doesn't go up much when X is really big, because we've got the rate of change approaching 0 when X is really large. So yeah, revenue increases when you make more machines, but it increases at a really small rate when you make X large, when you make a whole bunch of the machines. In fact, we could go through and see that the revenue function has a horizontal asymptote of 20,000. So realistically, you might want to cap the number of machines you make, because there's something called a point of diminishing returns. It's not really worth the extra effort to produce more and more machines, because the revenue, though it'll increase a tiny, tiny amount. So there's an application to economics and that thing in terms of approximations. Let's do one last example. This time, idea of inflating a balloon. They'll give us a formula. They'll ask us some stuff about rates of change. We're told the volume of a balloon, a spherical balloon, is 4/3 pi r cubed. That's a formula for the volume of a sphere. Volume of a spherical balloon changes with radius. At what rate does the volume change with respect to the radius when r equals 2 feet? Rate of change, that's a derivative question. Rate of change of volume with respect to radius. That'd be a dV dr question. Derivative of the volume with respect to radius, when the radius is 2 feet. And then they ask us about an approximate change again. And we'll work this one similar to the previous one. Question specifically being, by approximately how much does the volume increase when the radius changes from 2 feet to 2.2 feet? So the radius changes by 0.2 feet there. More of that in a second. Part 1, you want a rate of change. Rate of change of V with respect to R is the derivative of V with respect to R. V is 4/3 pi r cubed, so it'll be the derivative of 4/3 pi r cubed. We get the 4/3 pi constant stuff, r cubed, differentiate, 3r squared. You want to clean this up? Yeah, I'm going to have to plug a number into it. So let's clean it up a little bit. I can cancel the 3's, and then we're left with 4 pi r squared. Yeah, 4 pi r squared. Observation here, V is measured in cubic feet because it's a volume. R, what we have, I want to say in the denominator over here, really got to go to the difference quotient to see a denominator, but we differentiating with respect to R. R is measured in feet, so we'll indeed have cubic feet per foot. dV/dr is measured in cubic feet per foot. I really don't want to simplify that. I got my reasons. They told us something about cubic feet per feet up here, so let's leave it like that, even though awfully tempting to just write that as square feet. It's a rate of change, and I'd like to leave it in those units. They did it. When r equals 2, we're going to plug 2 feet into the derivative. Okay, I think this may be the first time we've used this notation, where we've got dV/dr, the derivative of v with respect to r, which we know to be 4 pi r squared. We're going to evaluate that at r equals 2. So this little vertical line means evaluated at whatever you've written down here. We'll use this symbol a lot in chapter 5, and a little bit in chapter, or wherever we are, chapter 3. This will pop up a few more times. But it means take the derivative and evaluate it at r equals 2. Here's a derivative, 4 pi r squared, r equals 2. That gives us 4 pi 2 squared. That gives us 16 pi, and we saw that the units would be cubic feet per feet. They wanted to know the rate of change. I should have put that in a box. There's the rate of change at that point in time. Part B, for r changing from 2 feet to 2.2 feet, how much does r change by? What's delta of r? The change in r, delta of r is 2.2 minus 2. It went up by 0.2 feet. As we had before, we're going to take, to approximate the change in volume, question being, approximately, how much does the volume increase by? We're going to take the derivative, evaluated at 2, and multiply it by the change in r, just like we did with that revenue function in the washing machines. The derivative of v with respect to r, evaluated at r equals 2, we just saw that was 16 pi from the previous part A, cubic feet per foot. We've got a change in r, delta r, of 0.2 feet, changed from 2 feet to 2.2 feet. It went up by 0.2. If they were deflating the balloon, we'd have a decrease in the radius, and we'd have a little negative number here. But in this case, it's gone up. So we get a 0.2 feet for the delta r. Let's cancel the feet in the denominator with the feet here to be left with cubic feet. And it looks like we get 3.2 pi cubic feet. I don't know if that number means too much to me, but do the units make sense? What was the question? How much does the volume increase? Yeah, volume's measured in cubic feet. Yeah, the units do make sense. The magnitude of the number, I don't have an intuitive feel for. Sometimes we will, sometimes we won't. When we do, I'll certainly point it out. But it looks like we get 3.2 pi cubic feet as a change in volume, and it's an approximation. And if you don't like this taking derivatives and multiplying by little changes in the independent variable, yeah, I'm kind of right there with you. We'll clean this up a little bit more, this approximation stuff. We'll clean up in section 3.11 right at the end of chapter 3. But that gets us through derivatives as they relate to positions, velocities, and accelerations. So useful stuff, physics stuff. If you're in chemistry, you'll deal with rate equations in chemistry and physical chemistry. If you're in physics, you'll deal with the stuff in physics, probably some of the same stuff we've seen. You'll likely take it into higher dimensions, 2 and 3 dimensions. And if you're in engineering, you'll take a dynamics class where you deal with things that are moving, things that are dynamic. And these derivatives will be all over the place, describing velocities, accelerations, and forces in the dynamics classes. The forces stuff will even come up in the statics class where things ain't moving, but there's still forces acting, and there's still accelerations related to gravity at the very least. But that takes care of our obligations on this section. We'll see you in the next section. Have a nice day.